Okay, so um, all right. In case anyone just joined, I did post the link to the worksheet um, on GitHub in the chat. It'll be a good idea to have the worksheet up while we're doing the problem session because I won't be showing it on my screen. I'll just be showing something to scribble notes on as we look through it. Um, so, okay. So yeah, you guys can continue to use chat to talk with each other during the session. I'll try looking at it periodically if there are any specific questions for me. I think as long as there aren't too many people here asking questions, we could also you guys could also interrupt me from time to time just over audio so that I can hear any questions you have. All right, so let me share. Let me just share my screen. Okay. I think you should be able to see a notebook app on the screen. Okay. So I was thinking we just get started with the worksheet, starting with the first question, going one by one. And then we'll take it from there. All right, so, okay. So my handwriting is gonna be a little messy, but just bear with me. All right, so problem one. All right, so this question is about defining what's called the standard finite types. So this gives the first definition we're gonna look at. Sorry, something. And then, all right, so we see that from the worksheet, we see that we have two constructors to inductively define this family of types. So we have a point constructor. This takes a natural number, and then it returns an element of the successor of that number of the finite type. And then we also have this inclusion map, which we'll denote by I, that takes a natural number and returns a function that takes a finite type of n and returns a finite type of successor of n. Okay, so the first question asks us to explicitly write down what the elements of fin 3 will be. All right, so okay, so when we look at these inductive constructions and we want to think of how we can construct elements of them, the first thing we should do is always see how can we start? What's our base case from which we can start constructing elements? And in this case, we have these two constructors, point and I. I requires us to, in order to construct an element of a fin type, and the output will be this fin successive n, we already need to have given an element of fin n. So we can't really start there because we don't have any elements of any of the fin n yet when we're starting to construct the elements. So in that case, point looks like the better option. So could someone tell me how we could apply point to get an element of fin3? So let's remember 3 is, this is exactly the same thing definitionally as, this is just shorthand notation for successor of 0, right? 0. So fin3, sorry. So fin3 is exactly the same thing as fin successor 2. So to construct an element of fin3 with our constructors, and we're looking at point to start here, how do I apply point to get an element of fin success 2? Okay, I don't know if there's any. Oh, is there chat? Sorry, is there chat? Sorry about that. Yeah, okay. Sorry about I need to check chat more. Okay, so now I'm seeing more chat. So okay, all right. So I'm looking at the first comment in chat, Maxime. A recap on universes. If there's any time after we look at this worksheet, I think we could talk about universe a little bit. But I think the session is dedicated to looking at this worksheet first. So there's not much universe specific stuff on it, but maybe later. Okay. And then, okay, I just want to acknowledge that, yeah, point 2. Exactly. We can apply this point constructor to the number 2, and that, by definition of the map, gives us an element of fin, which is exactly what we wanted. So that's one element. So now that we have the base case, we can try to use the actual induction in the construction of the fin n types to get more elements. But before that, let me. So it's an inclusion map, basically an injective function. No, actually, all right, I did say inclusion, and I think that is the connotation with the letter I too. In this case, it actually is going to be an injective function, but a lot of times inclusion is meant a little more loosely. In general, when the word inclusion is used, it need not be injective. This is more generally, this is similar to maybe if you're familiar, when we have coproducts in category theory, we'll often talk about a map from the canonical maps from each factor into the coproduct. Maybe we'll call it an inclusion, but in general, coproducts, it need not be the case that those inclusion maps into the coproduct are monomorphisms, or in some cases that reduces the injections in certain categories. Okay, let's see. All right, so let's look at some other possible elements of fin3 we can construct. So we have this point 2. We can't do much else by just applying point right now. So let's look at the map I. What are some things? So we have an element of so okay, so we in order to apply I, we're going to need a natural number and an element of fin n. So in this case, fin n, what is fin n? Remember, we want fin's successor of 2 as our final type, as the type of our final element. So fin, so instead of fin successor 2, we want the predecessor of the successor 2. So we need an element of fin 2 as well. So we're going to need an element of fin 2 and apply I to, and then we can apply I to get an element of fin 3, and then we so if we apply I to 0.2, then what are we going to? 0.2 is in fin 3, so we're going to end up with an element of fin successor of 3. So that would be fin 4, which we're not going to want. So that's a little too high. Oh yeah, right, okay. So now instead we say I.1. So yeah, you're leaving the first parameter implicit, which is fine. But so I'm going to put it in. But yeah, I.1. That also gives us an element of fin 3. Because 0.1 is an element of fin successor 1, fin 2. So then I applied to an element of fin 2 gives an element of fin 3. So good. And then, as you might expect, we're not quite done. I mean, fin 3, as the, you know, as we think, has one more element. Can anyone construct it using I? Yes, yes. The first thing to notice, as we see in the comment, is that in order to get fin successive 2, i.e. fin 3, from I, we're going to need to apply it to fin 2. So yes, it's going to have the form I2. Yeah, yes, that's correct. I'm just going to put in the implicit first parameters in the answer in the chat, but yeah, we're going to have I'm missing a parenthesis. All right. So yeah, those are those are the 3 elements that we can construct a fin 3. There's no other way to construct more elements. You might want to play around with that, thinking about that. If you doubt that, if you think that there might be another way, play around, and you should see a way. You should see maybe a mistake you're making. But I'm gonna, for time, I'm gonna move on because this next question is a little more in depth. All right, so let's see, problem 2. So let's see. So problem 2 gives another definition. And so this problem 2 gives another definition, and I should note already that we're going to need to refer back to the to what's mentioned at the bottom of problem 1 about this induction principle that you derive from this inductive type family in problem 1. 0. Okay, so there's a question: is 0 the empty type? No. So far, okay. I'm switching around, so I don't know what you're referring to. If you're referring to so let me write it down. We've seen 0 represent the natural number 0 so far in problem 1, but now we have a new definition of of the fin of how we can define the standard finite types fin prime. And the first case, the base case is the empty type. It's actually not just equivalent. So fin prime here, the fin prime is not just equivalent to the empty type, but we're defining it to be the empty type. So it's judgmentally equal to the empty type by definition here. And then, so now fin prime successor of n is recursively defined as the previous fin, and then you take the coproduct with the unit type. So okay, so that's our new definition. And we're helped out a little bit here by getting some suggestive notation. We're gonna denote by I prime so we have these two since this is a coproduct, since fin prime successive n is a coproduct, we can form our usual coproduct maps, and we're gonna, in this case, denote okay, sorry, I should have so the first one, fin prime n going into fin prime successor. So, and then we also have the right inclusion, the right coproduct map, which we'll denote by point prime. And I probably should be adding, you could add n subscripts on both of these to be extra precise, but often we get lazy and don't. And so this will be so this we can just write as an element of fin prime successor of n, because we're basically leaving out the canonical element of the unit type as a parameter. We're just leaving that out. It's equivalent just to write this as we're just writing, instead of a map, we're just writing this as an element of fin prime successor n. Okay. So now let's look at okay, so now it asks us to formulate the induction principle of fin prime. So I interpreted this question in the way I'm going to go about looking at this this induction principle is as follows. I'm going to I think what I'm going to do is we're going to write down the induction principles that were given from the definition of fin prime as a function from the natural numbers. And then we're going to derive an induction principle of the form given at the bottom of the first question for fin prime. Note that the induction principle of the first form from the first question is given for fin in the first definition of fin. So we're doing something new here. We're going to derive this form. We're going to derive this kind of induction principle for fin prime. Okay, so let's see. All right, so let's here, maybe I have a little more room. So okay, so we have this this new definition fin prime out of the natural numbers. So let's see what. So we're automatically given induction principles for the natural numbers, and it will, in this case, it will look like this. So suppose that we're given two pieces of data. We're given F naught, which will be a map. Oh, sorry. Which will be a map from fin prime 0 to some predicate. So okay, I should first say that we're trying to define a predicate that's going to take a natural number n and a element of fin prime and it's going to give us back a type. So I'm going to write the universe U here. But if you're more comfortable, you can just think of P being a type expression depending on a natural number n and an element x of fin prime of n. It's exactly the same thing as the notation from the first induction principle from page 1. Okay, so the induction principle on natural numbers will say that if we have f0 and we have this other function f sub n, which says that if we've already defined this function for n and from that we can get a new function that takes so we've already defined the function that we want for n, and from that we can get a new function for successor of n. So if we have that, then we get a function for all the n of the form we want. Okay, so this is a G. So yeah, so we get so this is what the induction principle in this case for natural numbers tells us. Now we also have computation rules. Sorry, I need to. All right. So we also have computation rules from the induction principle, and it says that this function we get will definitionally agree with the f0 data on 0, and on successor it will definitionally agree with f sub n applied to the previous g of n for all x. So this is just from the natural number induction, and now we can expand more. from this, because there's a special, because it's not that for every n, the predicate takes in an element of fin prime of n. And just looking at a question in chat, does this? Yeah, well, yeah, you could. So it sounds, maybe I'm misinterpreting your question, but it sounds like if we're looking at a p that's defined on just a finitely many natural numbers, like 0, 1, 2, 3, but not all natural numbers. Yeah, you can get, yes, I mean, you can get an induction principle that you basically expect. Remember, Booleans is basically this special, what you're talking about in the special case of just two natural numbers. And that has an induction principle that I think we've looked at in the course. It's the same idea as that. Actually, like now, we're actually currently just defining these finite types that consist of exactly the range of numbers that you're asking about, fin 3, fin 4, fin 5, and we're actually looking at induction principles for those right now. So they're not the same as natural numbers, but they're what you'd expect, I think. All right. So okay. So as I was saying, like we have a special case here because it's taking the function for each n is taking in an element of fin prime. If we can use this version. I don't see how you. The one I'm currently defining is. So the one I'm right now currently defining is simply the induction principle for the natural numbers. So it's specifically applying to the axioms for the natural numbers and natural number induction we have. Okay.
Yeah.
Okay.
So yeah, what I meant is like if we want to use if I want to use a value of fin type, and the thing I want to use them for only works like with the specific number 3 or lower or something like that, that still works with this definition of the induction principle.
I might not completely understand, because are we talking about replacing the natural numbers with
no?
No. Okay, you're talking about.
Yep.
I see. You're talking about if we only know fin prime if we only have defined fin prime for finite.
No, I think I'm just meaning if like the p I want to get out of the induction principle. Yeah. If that only works for like low number, because like the way I look at the definition of it looks like I need to be able to define it for all n, not just for a specific n, but maybe I'm like confused in which the direction, if it's just that induction says that this works for all n and not that it requires you to define p for all n. That's kind of.
This induction principle does require that p is defined for all natural numbers n.
Yeah.
Okay. Does that clarify it at all?
Yeah. So in the, I guess like if the concrete thing we want to do only works for like the smaller numbers, then we would just have to define a p where it's a nonsense value for for n that's larger.
Yeah, you could. Yeah, you could. I mean, if you have exactly. I mean, if you can specifically define p for a certain finite range of natural numbers, if you can explicitly do that, then then you can do that, and then you could, and then for all the remaining natural numbers, you could define some distinguished value for it. Yeah.
For example, if I want to make a function that maps FinOf to bool, how would I do that? I guess in that case you would just have a constant, so that's why it works for every natural number.
So okay,
we can take this later maybe if it's
okay. Yeah, I might not be completely understanding, but yeah, maybe after I do this, the rest of this, maybe I can try to answer it again. Okay. So we can do more with this, with our induction. We could do more with what we get from the induction principle for fin prime, because the little x is coming from fin prime of n, which itself is defined as a coproduct. So we also have an induction principle for coproduct. So we can unfold more and then okay, so now I want to let H be a map from fin prime of n to our predicate p sub n of x, and suppose we've constructed okay, I guess I need more. Sorry. Okay, so suppose that we've constructed two terms, T1, which is a map from fin prime of n to p successor of n on I prime of y. And then let me write out the second one. So T sub 2 will be just an element of P sub successor of n on the point. And I'll write, for clarity, I'll write the subscript n, which I dropped earlier, I think. But okay, so suppose that, suppose that this is the function, suppose that our function from fin prime of n is defined in this way. The induction principle for coproducts says that that maps out of coproducts are characterized by functions from the first factor. By a function from the first factor and a function from the second factor. So that's what T1 and T2 are describing here. And in that case, so now we can augment our computation rules from before for little g that we got. So now we can actually say that g on successor of n on I prime of y is judgmentally equal to, so this is what we had before, right? This is from the computation rule we wrote down before, but now we know from the computation rules for coproducts that this is exactly T sub 1 on y. So so let's see, okay, so let me just, so these are the G's. Okay, so now, okay, so so that's the first new computation rule. And we also can say that G on the successor of the point is, as before, we can write it as G, f of n on G of n point prime. And now this becomes f sub n G of n on T2. Okay. So this is what we get after unfolding all the computation rules we have from the induction principle for natural numbers and then the coproduct. And those are the two type formers that are used in the definition of fin prime, right? So, okay, so this is what we have given to us. Now, what I want to do now, since we sorry, let me just make sure yeah, I see. Okay, so now what I want to do now that we have all this written down is, like I said, derive an induction principle of the form given on page 1 for fin prime now. So, okay. So, so what we're going to do is suppose that we have the data given to us as in page 1. So suppose we have oh yeah, I should say now that yeah, I think, yeah, I already can see that I'm switching up notation from the worksheet. I know that the worksheet uses little f for the function that we get and G sub n for the data, and I realize that my notation might be off from that a bit, so I apologize. But hopefully you can see how match things up. All right. Okay, so suppose we have a function, and I think I am actually, okay, so in this case, I actually am using the notation from the page 1. So suppose that we have G little n as the initial data, which has this oops. I prime of x. Okay. So so we have this initial function, and then we also have these initial points, which are elements of the successor of n on point prime. So okay, so this is the data that looks like the data from page 1. And now I want to derive a function with the computation rules for fin prime as described in on page 1. Okay. So okay. So so I want to, so okay, so so I want to apply the induction principles for natural numbers and coproducts as I did before in order to construct the function with the computation rules that I want. To that end, I'm gonna again let little h be the hypothesis of the natural number induction rule that I want to use. So to use the natural number induction rule, we need to show that for any function of the form little h here, we can construct. We need to construct a function f sub n that depends on little h that has the type fin prime successor and this okay. So we need to construct such an element depending on little h. And if we can, then we can apply the induction principles as before for fin prime, given by the natural numbers, and then afterward by the coproduct. Okay, so how are we going to define this? How can we construct a function like this, given the data that we have? So let me write it out. So in order to use the computation rules for the coproduct, I'm going to want to define this function here by induction on the coproduct fin prime n plus the unit type. So let me, let's see, how should I write this? 1 second, let me, okay. Let me write it in this notation. So by induction on the coproduct type, that should be y. I have two cases to consider. I have the inclusion case and I have the point case. Sorry. And I have point prime. So I'm going to need to define two terms here. So can anyone tell me how we might do one or both, or any ideas for this definition? Okay, let's first, just to clarify, let's start with the bottom one. It looks a little easier. So, what this is going to have this has type so this bottom one, the element that we're defining for it needs to have this type, P successor of n on point prime. Do we have any data given to us that has this type? Okay, I think part of this is the issue is the layout of these notes is a little bad. So I'm going back to the previous page. This might jog your memory. Let's look. Remember, this is the initial data from the induction principle that we want to derive. This is the initial data we're given, these two terms. So what can we do? Okay, let me see something. Okay. Anyway, all right, so all right, I'll move on from asking and just kind of show what's happening. So we have this initial data. Let's look at this. The second one, Pn is the given data, and it has exactly the type that we want. So we can simply, for the second one, write P sub n. So the first one, similarly, we're going to look at what we have from Gn, and Gn takes in an element of fin prime n and an element of Pn of x, and it gives out P successor of n I prime of x. Okay. So you can check that we can plug in y and h of y to g little n, and this will type check as we want. So remember, h of y is going to be p sub n of y, and we can, so that can be the second argument, this one to g little n, and that will give us p successor of n I prime of y, which is exactly the term we have here. Okay, so that might be something just to type check on your own afterward to make sure it works. Okay, so we've defined the term we need, and since we did that, we can apply natural number induction to get. So now we get, and again, sorry for the notation, but I'm gonna put it, I think it might clean things up if I put a new letter, little k. So now we get from natural number induction, we get a term on all the natural numbers that takes in an element of fin prime of n, and we get back the predicate we want. Okay, so that's the general function we get from natural number induction based on what we did. Now, the interesting part might be the computation rules that should align with the computation rules from page 1. So computation rules, and we're applying the computation rules we derived from natural number induction with coproduct induction from above that we did earlier. So the computation rules say that so I got a question. Didn't we get the same thing with fin and fin prime? Could you clarify? Because right now we're trying to get the same induction principle for fin prime. that we had for fin. Well, right now I'm proving, to be precise, what I'm proving right now is that I can derive an induction principle of the form from page 1 for fin prime. The induction principle from page 1 is for fin. Okay, just in the you can keep, we can return to this question. I just want to make sure I write down the rest of it in the interest of time. On the successor of n, and then furthermore, when we pattern match on the I prime of y, we get judgmental equalities with f little n applied to the previous k of n on I prime of y, which in turn, by coproduct computation rules, is we can go back to the original data, g little n, that we had on y of the previous. Sorry, I didn't write this correct. Let me get rid of that. Okay. All right. And then furthermore, on the point, so this is still on this is behavior on the successor of n, but now on the point, this is the other coproduct computation rule. We can derive judgmental equalities on k of n point prime, and now this will be exactly p of little n. And these last, and so this one and this one come from the way that we defined the f of n on the two cases for the coproduct. And this all ties back into the computation rules, the general computation rules we derived earlier from natural number induction and coproducts. Okay, so what's the upshot here? The function little k that we get has exactly the computational behavior that that little f has on page 1. So we've derived this form of an induction principle from page 1 for fin prime. Okay, so this might have been a little fast, but one relatively straightforward application that you have with this form of the induction principle for fin prime is you can define a map back and forth between fin prime of n and fin of n, and show that in particular the maps back and forth will form an equivalence. So in fact, as you might expect, the two definitions for each n, for each finite type n are the same. Okay, let's see. So that was I think that was in my opinion, that was the longest one. Okay, let's see. We have a question in the chat. Yeah. I mean, okay. I mean, you would use the induction. The way that you would use the induction principle is. Okay, I see. I think I see what I kind of see what your question is. So let's look at the induction. So let's look at this induction principle from page 1. It is true that you need to define this predicate P of n, P sub little n of x on all n. It requires it to be defined on all the natural numbers. It's doing induction simultaneously on all the it requires the entire natural numbers at once to perform the induction. Okay. Anyway, so yeah, that was so moving on a little bit. Question 3 gives a direct application of the induction principles that we just defined. Let's look at, instead of giving, let's use the induction principle that we just got let's just define one of the, yes, you could do that for all n, and for all x, you can define it to be constant bool. That gives you a predicate that you can use. Okay. Anyway, so for question 3, let's just look at one definition of an inclusion map. Okay. So so the notation is iota. So let's define for each natural number, we get a function from the finite. All right. All right, so let's, so using induction that we got, how could we, so basically by induction, what we really mean is pattern matching with the judgmental equalities that we got from the induction principle. So that requires us to give a definition of 2 terms. So let me, so we need, so from the induction, from the computation rules, let's say from page 1 at the bottom, we need iota of successor of n on, we need it on, sorry, that doesn't look very, let me clean that up. So we're gonna need it on point, and we're also going to need it on the inclusion I of x. So so maybe we can start with the point one. If we're trying to get a function where the image are the first n+1 natural numbers, which one way we can, we're going to need a natural number for each slot here, because that's our output type. So for the first one, what natural number could we give? Yeah, 0, that works. And then how about for the second case where we have the inclusion? Remember the judgmental equalities, the pattern matching that we got from the induction principle says that we can do recursion here as well. So maybe that will help. So recursion will look like, it will look like taking iota of n and applying it to the x that we have nested, or to which the x is applied. So yeah, so successor of iota n, I'll put in the parameter of x. And yeah, that definition will give you for each n, it will give you the first n+1 natural numbers in the image. Okay, so obviously we're running low on time. I think a lot of the, in my opinion, several of the questions after this, up until maybe the last few, the last few or so, are mainly about translating, propositions, mathematical assertions into the type theory. So it might not be worth spending too much time on those right now. So yeah, I think at this, and then I'd say the last question, number 10, takes a little bit of time, although I don't think anything is conceptually too bad. So I think, given the time, I think maybe, is there anything in particular that I should talk about at the end here, instead of going, obviously I don't think I can go over the rest of the worksheet completely. Does anyone have any question or concept from the worksheet that I should focus on right now? Okay, so in that case, let me shoot. Okay, then it might be, maybe it's instructive to go over one of the translations I was talking about. So let's look at question 5. So problem 5. So we want to define is prime. So we want this function that takes a natural number, and it's going to return a type okay, so so let's think, what does it mean for a given natural number? What does it mean for it to be prime? We want to give a type that when we have an element of that type, it captures exactly what it means for the natural number n to be prime. So it would give a proof or evidence that the natural number n is prime. So there are multiple ways. What are some components of being a prime number that we want to make sure we capture? It doesn't need to be the whole thing. I mean, it could be, but what's one feature that we want to encode? Yeah, so yeah, all right, so not having any, I guess, non-trivial divisors, right? All right, so let's try to write that in. So so we need a type. So So okay, so let's try to translate a type that says the number is not divisible by any number except itself and one. So any ideas on that, on how we can use our type formers that we've seen? Even if it's not a precise description, we could just start building it. Okay, so all right, so let's so I guess one so there's a few ways you might think about doing this. You might try to directly say that there, you might try to negate like an assertion saying that there is a number that's not equal to 1 or n that divides n. That's, that might, negation can be annoying to work with because we're in a constructive logic. You might not be able to derive all the properties that you want or expect to be able to derive of your definition of is prime. So instead of negation, let's try to like give a positive definition, positive evidence of the number being prime. So so let's say, suppose that we have a natural number m, and let's assume that it violates let's assume it might violate the property of n being prime. So yeah. Wait, k equals. Yeah. Okay. I think you'll just need to. You'll probably need to get. You'll need to get rid of the case when n can be 1, right? So I guess you can just exclude that case by saying n is at least 2. Okay. Okay. So yeah, I think that'll work though. Okay, I think that would work. Another one that I was going to translate from the first suggestion is something that says that if m is a number that, and actually, yeah, I guess I am using negation inside. Okay, I am using negation inside this pi type, which I said negation might be hard to work with. It turns out that natural numbers can provably have decidable equality, so it's not too bad here. But yeah, okay. But so say it doesn't equal n, but at the same time it does divide it. So recall that conjunction takes the form of Cartesian product, so that m divides n. Okay, so yeah, so that condition will hold. Then in order for it to be prime, M is going to have to be 1. And I think yeah, you also could add by implication here. Yeah. Okay. So, all right. I think. Let's see. I think, would we use? Okay. Yes. Oh. No, you. No, you. Well, you don't need to, but yeah. Yeah. I mean, if you just want to look at the finite numbers, I mean, sorry, the finite range of numbers less than or equal to n, that would be, you could, I mean, yeah, you could do that, and you would get an equivalent definition. You would have to, you might have to, in order to prove all the properties you want, you might have to prove some things about division at the start. But I think it would all come out the same ultimately in terms of what you'd have to prove for the properties you want. You'd have to prove that no number greater than n can divide n. If you want to prove some things about your definition of is prime. All right. So yeah, are there? I mean, it would be good. I mean, are there any general questions now? That I could answer about anything from the worksheet or related concepts from lecture or something else? Is there a specific question on the worksheet that people wanted to make sure I covered? So inclusion in type theory. I was talking about this a little bit at the start. I don't think it always has a precise definition. A lot of times it can genuinely mean that. So it would be a function from one type to another, and sometimes you can genuinely prove that it's injective in a certain sense. But a lot of times it's kind of a suggestive term too. That isn't always provably injective. Like I was saying with the inclusions from a factor of a coproduct into the coproduct. It's not always a monomorphism, but we still say inclusion sometimes. All right, let me see. There's a few more questions. So how to define an equivalence fin for, sorry, what is that? SUI suit? Could you say what fin for to what? Okay, am I ready? Sorry, that might, I'm not meaning to write. Yeah, I'm not, am I writing like conjunction, disjunction kind of thing? No, I kind of am. I wasn't thinking of doing that, but that's kind of how it looks. It's supposed to be a Blackboard N. Oh, Is the theme of this? Okay, is the theme of this worksheet functions of the form? I don't think that's not necessarily the theme. Also, now that I probably should to be consistent. I think I now see that I do want to. Not that it really makes a difference, but instead of capital U, I think this worksheet's been using type for that. So yeah, I did want to clarify that, but yeah. So I mean, this type is a universe. So you're right that this things that we covered on this worksheet wouldn't make sense without being able to define these functions into type. I'm not sure if it's the theme, but it is something we're using, definitely. Okay. So yeah, okay, let's see. We have this function. Yeah, those are the elements of fin4. Yeah, the previous lecture did cover universes, and we're using it now, and I think we'll be using it basically constantly from now on. It's the way we define, as you can see, it's the way we construct properties of I mean, it's the way that we construct predicates on types. Yeah, that looks like that looks like a valid definition from fin4. Yeah, yeah. I mean, you're basically, yeah, you're unfolding the pattern matching from the induction principle on the finite types. And then, so okay, the question was, it was an equivalence. Yeah, you're gonna want to just define a function by pattern matching on suit back into fin4, and then prove that they compose to the identity. And then to prove that they compose to the identity, you're actually going to want to form a type P of little n of x that asserts that they compose to the identity, and then prove that that's true using the induction principle for fin. Let me just see if I missed anything else in chat. I don't, okay. I think I did get to everything. Okay, yeah, so I think we could call it now. Yeah, so yeah, that's all I have. So thanks everyone for showing up. And I'll end the recording.